Okay. There are two kinds of electrons, valence electrons and core electrons. For main group elements, and that's primarily where we talk about them, the valence electrons are those in the outermost principal energy level. So whichever electrons have the highest principal quantum number, n equals 1, n equals 2, whichever one's the highest. And the group number tells us the number of valence electrons that that element has. And that group number is the US group number with the letters. So 1A, 2A, 3A, those. That's why I prefer them. It tells us the number of valence electrons. Electrons in the lower energy levels are called core electrons. So they're like the apple core. They're on the inside. The valence electrons are on the outside. And one of the very important factors in how atoms behave, both with chemical properties and physical properties, is how many valence electrons do they have. So here are the first three rows of the periodic table. And we see the electron configurations for that highest energy level. So hydrogen is 1s1, helium's 1s2. Hydrogen and helium don't have any core electrons, and so their valence electrons are just the number of electrons. So helium is acting like the baby brother and being out of place over here. These group numbers tell us the number of valence electrons, but does helium have 8 valence electrons? It's in group 8. No, it can't have 8 valence electrons. It only has 2 electrons. So he kind of breaks the rules. Lithium. Lithium has this 1s2 level full, and then he's got one more electron in the 2s. And so that's 1 valence electron. And as we go across the periodic table, we think about just adding one more electron. So if nitrogen, his electron configuration ends in 2s2, 2p3, we add one more electron. Where would it go? It would go in the 2p4. Add another electron. It'll fill up the 2p, and it'll have 6 electrons. So neon has 8 valence electrons. It's in group 8. If you think about the noble gas shorthand configuration, this would be helium plus whatever's written under the element symbol. So for chlorine, chlorine has the electron configuration of neon, and then in addition it has 2 electrons in the 3s, and 1, 2, 3, 4, 5 electrons in the 3p. So it has 2 plus 5, 7 valence electrons. How many valence electrons does silicon have? 4. How about beryllium? 2. It's in group 2. The group number is the number of valence electrons. The reason that fluorine and chlorine have many similar properties is that they both have 7 valence electrons. The number of valence electrons explains this recurring pattern of properties in the periodic table. The noble gases, they're very inert, right? Except for helium, they all have 8 valence electrons. Helium only has 2 valence electrons. What's up with that? Well, that first level is full. Here, the second level is full. Here, the third level, full. And so there's something magical about that. It's not magic. Any questions? Yes?
And the transition metals?
Transition metals are weird. Most of the transition metals have 1 or 2 valence electrons. I think we'll get to talking about them. Again, I want to come back. Well, no, I want to come back. Okay, this is the good stuff. Electron configuration of the periodic table. We can divide the periodic table into 4 different blocks that represent the filling of 4 quantum sublevels, S, P, D, and F. The group number for a main element is going to be equal to the number of valence electrons for that element, and the row number is going, the period number is going to be equal to the highest principal quantum number of that element. Ta-da! Okay. How many electrons can fit in the S sublevel? 2. Look, there's 2 columns here. They kind of stick up. This is the S block. How many electrons fit in the P sublevel? 6. How many columns here? 6. This is the P block. How many electrons fit in a D sublevel? 10. How many columns? 10. How about the F? 14. How many columns? 14. Is that cool or what? This is not coincidence. This is not us drawing the table to fit our quantum mechanical theory. The periodic table looked like this before we had any idea that quantum mechanics was a possibility. It was drawn up, it was organized that way based on increasing mass and periodic properties. We end up with this, and then years later, quantum mechanical model says, oh, that's why it is like that. So here is the filling. So here's the period number 1. That corresponds to N. So N equals 1. So hydrogen is filling the 1s, it's the S block. Now helium's got to be a little squirrely and be over here. He really should be over there. But we can deal with it. S2. And so then we come to level 2. So now we're filling the 2s or sublevel. 2 electrons can go in there. And then we go on to the P sublevel in level 2. And so we fill 1, 2, 3, 4, 5, 6. And then we go to N equals 3. There's 3s and 3p. And then we keep going. And what happened to 3d? Oh, well, here's 4s. Now this is the D part. This is where things get a little ornery. Here we're going with N minus 1 for these guys. So this is in period 4, but this D block, this is 3D1, 2, 3, to 3D7, 3D10. And we get over here back to P, and this is in the regular. I think of this transition metal part as being sunken, right? It's below maybe where it should be. I see this and I think, done, we're going down the steps. Ooh, that was a big one. I would like it to be up here, and then it would be 3D, but that's not how it is, and that's due to interactions. So here's 3D, 4p, next is 5s, this again, N minus 1, 4d, 5p, 6s, and here's 7d, and then we get this little gap here. This is lanthanum, 57, 72. We need to jump down here. The periodic table on our wall, because it fit better, we've got it the way it really should be. You take the periodic table and you cut it right here, and you spread it apart and you stick these in here. And then you've got 57, 58, up to 71, and back to 72. So this F group, F block, I should say, those are N minus 2. So whatever the period is, subtract 2. So this is coming from period 6. 6 minus 2, this is filling the 4F. So 4F is filling up here. When that's done, we get back to 5D, 6P, 7S, a little bit of 6D, and then we go to 5F and 6D. And you can actually keep going because now we have them all the way out. So the order is all hiding in here. Do you need me to show you that again? It's going to take a little practice. This is my husband squawking in the hallway. Any questions? Is that cool? That's better than memorizing stuff. Okay, now that we know this, let's go back to those examples we skipped. So the electron configuration for chlorine. A good thing to ask yourself first is, how many electrons? 17. 17 electrons. So we're going to start at the beginning and move along. And the periodic table is going to help us with the order. So first is 1s, and we'll put 2 electrons in there. And next is 2s, we'll put 2 electrons in there. And 2p, and that's going to have 6 electrons. And what's next? 3s, 2 electrons. And then what? 3p. Now, you could figure out how many by adding up and seeing how many you have left, or you can look at it on the periodic table. I need to edit this better. So here's chlorine. Chlorine is over here in the third period of the P block. So this is 3p, and it's over 1, 2, 3, 4, 5. So it's going to end with 3p5. It wasn't my husband either. His voice is lower than that. Any questions about that one? Okay, silicon, how many electrons? 14. Okay. 1s2, 2s2, 2p6, 3s2, 3p2. So 2 plus 2 is 4, and 6 is 10, and 2 and 2, 14 electrons. The order is on the periodic table. Okay, strontium. Strontium's a big guy. 38 electrons. 38 electrons. So they all start out the same, don't they? It does get tedious. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. What comes after 4s? 3d. Remember, it's sunk. So it's down a level. So 3d fills next. And how many electrons fit in the d sublevel? 10. If you forget, count the rows of those transition elements. After 3d, we get back to the fourth level, 4p. That's going to fill up with 6 electrons. And after 4p, what do? We come around to the 5s, and we need 2 in there for strontium. When we find strontium on the periodic table, it's almost, I'm sorry, that's barium, strontium. It's almost like a graph, and so strontium is in row 5, so 5 in the S block. So it ends in 5s. When you go to the D block, remember, like for ruthenium, this would be D, but it's not 5D, you have to subtract 1. So ruthenium's going to end with 4D. And the Fs, you have to subtract 2 from their group number. That's not too hard. Oxygen. Looking at the periodic table, what is the last sublevel that oxygen has? What period is oxygen in? What row in the periodic table? It's in row 2. In which block? S, P, D, or F? P block. So it's going to end with 2p. So oxygen has 8 electrons. So we go 1s2, 2s2, 2p, 4, right? Find oxygen over here. So it's 1s, there's 2 there, 2s, 2 electrons, and here's the 2p, 1, 2, 3, 4. This is important to be able to do this. Okay. Any questions? Yeah.
So are we ever going to do any with that go further into Fs?
Yeah, we're going to get there. Okay, so on to the next skipped example. Orbital diagram for argon, and determine the number of unpaired electrons. So electron configurations don't tell us, give us any information about spin or which ones are paired or not paired. And for some properties, it's important whether they're paired or not. So an orbital diagram, we're going to draw boxes. Okay? So looking at the periodic table, which sublevels do we need to draw? Up to 3p, right? Okay, so here's 1s. Here's 2s. P has 3 beds, so it's 3 boxes. So that's the 2p sublevel. And then we've got the 3s. Again, that's just 1 orbital. There's only 1 bed in the S room. And here's 3p. How many electrons does argon have? 18. So we're going to fill these up. And I seriously think about the electrons in the hotel when I do this. I'm going to make these guys red just for fun. So I'm going to count to 18 and fill this up. 1, 2, 3, 4, 5. Number 6 would rather sleep in his own bed. 6, 7. Now they're going to double up because sleeping together is better than spending more money. They're very cheap. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And you look at argon there, and this should be reasonable, right? Because argon's at the end of that P block, and so that suggests that it's full. Everything else before it's going to be full. Okay? Any questions? How many unpaired electrons? 0. 0 unpaired electrons.
So if this chlorine would just be 1 unpaired electrons?
Yeah, so what if it was chlorine? Well, chlorine has 1 less electron, so we take that one out, and then there's 1 unpaired electron. Okay. Electron configuration for phosphorus. Identify the valence electrons and core electrons. So phosphorus. Well, how many electrons does phosphorus have? It's got 15 electrons. And looking at its position on the periodic table, what does it end with? It's in the 3rd period, the 3rd row, in the P block, right? So it ends with 3P. 1s, 2, 2s, 2, 2p6, 3s2, and it's 1, 2, 3 over in that P block, so it's 3p3. Any questions? The only way you can get good at this is by actually doing it and then seeing, did I do it right or wrong? Okay, so there's the electron configuration. Valence electrons. From the electron configuration, what you're going to do is you're going to look for the highest principal quantum number. So this is 1, 2, 2, 3, 3. 3 is the highest number. It's all the things with the highest number. So it's the S and the P. So you find the highest principal quantum number, and then you find all of those. Those are your valence electrons. How many valence electrons? 2 plus 3 equals 5. I often abbreviate the valence electron as VE. Not to be confused with Victory in Europe Day, but VE. And when we look at the periodic table, what group is phosphorus in? It's in group 5A. That's not a coincidence. How many core electrons? And where are they? Well, it's the others, the ones in the lower levels. So there's 10 core electrons. These core electrons shield the valence electrons. Any questions? Did that. Okay. So this is a simplified version. So let's say we're trying to write the noble gas shorthand electron configuration for chlorine. Well, here's chlorine on the periodic table. Go up a row and to the end. Neon is the previous noble gas. So that's what we write in brackets. You got neon in brackets. And then you're going to add on what comes after neon. And so this is 3 in the S block. There's 1, 2. 3s2. And then we go over here to the P block. This is 3p. 1, 2, 3, 4, 5. 3p, 5. How many valence electrons? 7. The highest number here is 3. 2 plus 5 is 7. Chlorine is in group 7A. These group numbers, 1A, 2A through 8A, tell us the number of valence electrons for the main group elements. Any questions? Valence electrons are the electrons in the highest principal energy level, or the highest energy shell. So they're the electrons with the highest principal quantum number.
So we have the more number.
Yeah, so what if we were doing calcium? So calcium is down here, right? So calcium would be argon, 4s2, right? So in this highest level, 4s, those are the valence electrons.
Even if 4 appear before the 3?
Yes. Question?
Can you show me the noble gas configuration
Of iodine. Sure.
I mean, I'm not asking you to like completely. I asked for the noble gases. And the D's are the only ones that mix me up. So.
The D's mix you up? Okay.
Yeah.
So for iodine is right here. Yes? 2 below chlorine. So the previous noble gas is krypton. Not kryptonite, but krypton. Kryptonium. That's good. Blue, that's what I was trying to find. Blue. I'm just going to write this one in blue. So we've got krypton. And from krypton, we're going to come over here. And this is 5s2. So let's cross these off as we go through them. There's 5s2. And then we get to this D block. this is sunken. So it's not 5D, it's 4D. So 4D, oops, I'm lost. Up here. 5s2, 4D, and we're going across here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 4D10. You don't even really have to remember how many electrons can fit in the D sublevel, because you can just count the columns in the periodic table. And then, to get to iodine, this is P. This is not sunken, right? This is the sticking up part. So we're still in the 5, so this is 5P. One, two, three, four, 5. 5P5. Okay? Now, valence electrons. We have a 4 in here between the 5 and the 5. 4 is still a lower number than 5. We're going for the highest n. N equals 5 is the highest. So for valence electrons, it's these guys and these guys. 7 valence electrons. Iodine's in group 7. Any questions? Yes? It would be the number of electrons that iodine has minus 7. Everything else. So valence electrons are the ones with the highest n. Core electrons are everything else. Yes?
Would be, the 4010 being 4.
Yes, the 4d10 electrons are core electrons. And that's why the transition elements in here, as they're filling the D levels, they're not gaining valence electrons, they're gaining core electrons. Because these two at the beginning here, from the S, are higher in quantum number, and so they have the valence electrons. Okay, another example. Use the periodic table to determine the electron configuration of bismuth. Well, bismuth is down here. Right? Fun times. I just realized I should not have taken out the lanthanides and the actinides. Dang it. Never use those except in this slide. Anyway, okay. And it doesn't say noble gas, so we better do the whole thing. So here's one, those 1s2. And then this is 2s2. We're just counting, basically. Funny kind of counting. From here, we jump over here. This is 2p. There's 6. And then this is 3s. 2. We come over here. 3p6. And 4s2. And now this is the D block, right? So this isn't 4D, it's 3D. 3D, we count across, we've got 10. We get back to the main group, we're back to the just N. So this is 4P, and there's 6 there. And we come over here, 5S, 2, and then in here, this is 5 minus 1, 4D10. After 4D10, we get to 5P6. And then 6S2. Now, here's 1 in the 5D, but then it jumps down here to the part that I foolishly cut off. That's the F. So I'm in 6. I'm trying to get F. It's 6 minus 2, 4F. We're going to go all the way across that. If it was visible, it would be 14. So So we go all the way through those guys, and we come back up here. This is back to the Ds. Now we're going to pick up that one guy that we kind of skipped over. Ds are 6 minus 1, 5, so 5D, 10. And then over here, this is 6P, 1, 2, 3. Phew. Is that nice?
Are you,
Yes.
on the test, are you going to make us go like all the way down to the bottom?
Probably not.
You know, for room's sake?
So on a test, I give you a combination of multiple choice and show your work. There's really not a showing your work that's possible with this, and correcting something like that makes my head hurt after I've looked at 60 of them, trying to find the one little mistake. So questions like this will probably be in the multiple choice portion. There could be one like this. And there would be 4 or 5 choices, and you have to pick the correct one. Yeah. Any other questions? So that's all wonderful. Unfortunately, there are some irregularities. The S sublevel is lower than energy in the 3D, and so it fills first. We talked about that. But the difference in energy there is not very big. And so we sometimes have a situation where we disregard that energy change. In the quantum hotel, this is like some Groupon deal, right? There's a special on, and if you fulfill the requirements of the special, you get a discount. And so we'll see some irregular filling in order to accomplish the discount. What happens with this irregularity is that we get the s orbital, say the 4s, is only partially filling before the 3D does, or perhaps it doesn't fill at all. These electron configurations that are irregular have to be found experimentally. And we're just going to look at a couple of them. So these are some that are irregular. This is what we expect for chromium. We expect that it would be argon with 4s2 and 3d4. So let's look at just the valence orbital diagram for that. So here's 4s, and I usually do better than that. Bless you. And this is 3d4. I'm sorry, 3d. So what chromium's got going on here, what we expect is that it would go like this. So there's 2 in there, and then there's 4 here. But what actually happens is that there's only 1 electron in the 4s sublevel, and there's 5 over here. So I need to take this guy and stick him over here. Thinking of the hotel, why would the electrons like that better? Everybody's got their own bed, right? There is extra stability when you have this sublevel exactly half full or completely full. So there's a Groupon deal that if you've got half full rooms between the S and the D, or you've got completely full, there's some discounts available, okay? So that's one example. So this one does that, and molybdenum does that. We expect 4s2, 4d4. We get 5s1, 4d5, because then both of those are half full. Okay, let's look at, oh, I didn't need to erase that. Let's look at copper. Oh, I'm just a mess now. So copper, we've got 4s2 and 3d9, right? So 2 here, 1, 2, 3, 4, 5, 6, 7, 8, 9. You might say, well, what's the deal? Why not? Well, what it actually does is it takes this one and moves it up here. I look at this and I see better symmetry. And these are things that just help me to rationalize why this might happen so that I can remember. Now we've got this one half full and this one exactly full. Before, I've got this one exactly full and this one, it's so close, right? It's so close. So it's slightly lower in energy for it to do this. And so it does. So copper does that. And ruthenium, I don't want to talk about ruthenium. Ruthenium doesn't make a lot of sense. Palladium does kind of a similar thing. Here we've got S2 and D8, and both of those go over to the D. So we've got an empty and a completely full. The ones I want you to remember are chromium and copper. Those, you are responsible to remember that those are irregular in their electron configurations. Not remembering that will not cause you to fail the class. But A students should remember that. So any questions about the irregular electron configurations? Oh, what's next? What's next is that it doesn't want to let me change the slide. Don't understand. We're going to stop here.